Hello, my name is Yoonbyung Che. This is project presentation part 1 in application and practice in neural networks. And I talk about hierarchical attention network to refine human pose estimation in videos. First I talk about dataset. First dataset is AIST++ dense motion dataset. The dataset is constructed from the AIST dense video DB. It provides 3D human key point annotations and camera parameters for 10.1 million images, covering 30 different subjects in 9 views. These attributes make it the largest and richest existing dataset with 3D human key point annotations. Second dataset is PW3D. It means 3D poses in the wild dataset. The dataset is the first dataset in the wild with accurate 3D poses for evaluation. While other datasets outdoors exist, they are all restricted to a small recording volume. 3D-PW is the first one that includes video footage taken from a moving phone camera. And then I talk about baseline architecture. This is illustration of the denoise and recovery subnet. First, the sparsely sampled poses is denoised into a clean poses by a transformer-based denoise net to handle the dynamically various noises. Then, after a preliminary pose recovery, the sequence is embedded into temporal semantic pose tokens and put the tokens into another transformer-based recovery net that can leverage spatio-temporal correlations to recover realistic and natural poses. The sampled poses are obtained by single-frame pose estimators, inevitably leading to noise-sparse poses. In this reason, before running the representation, we select a pose estimator. A denoising network is developed to refine the sampled poses to clean poses. The key design of denoise net lies into two aspects: a dynamic model for handling diverse possible pose noises, global temporal receptive field to capture useful spatio-temporal information while suppressing distracting noises, transformer-based encoder modules to relieve noises from the sparse poses. The denoise process can be formulated as the first equation. Another linear projection matrix W is utilized to obtain refined sparse poses as the second equation. The runnable parameters in denoise net are trained by minimizing loss between clean poses and sampled ground truth poses. In order to learn the consistent temporal correlations, a simple temporal upsampling, for example a linear transformer WPR, is applied to perform preliminary sequence recovery to get clean preliminary poses. Temporal semantics are brought into pose encoding to encode the neighboring deep frames poses into pose tokens via a temporal 1D convolutional layer. The main architecture of RecoverNet is also the same as Transformer, which employs M multi-head self-attention blocks. As illustrated in the second block marked as RecoverNet in figure, key information is drawn in the cross-attention block by leveraging denoised features. Recent 3D pose estimation methods are followed to apply a simple L1 regression loss to minimize the errors between PT and PT head for 2D or 3D pose estimation. I proposed a simple methodology which is named cross-sampling. I additionally sampled among samples in baseline. This is for capturing detailed information. If in baseline samples in dice are 0, 4, 8, 12, and so on, cross samples in dices are 2, 6, 10, 14, and so on. Cross samples are passed into fully connected layer and later into transformer encoder, which is called cross encoder. As you know, in baseline, denoised features are utilized for recovering in RecoverNet. Instead, I use novel denoised features encoded from cross encoder. I expect that with this feature, RecoverNet can encode the information which baseline samples lose. If ground truth motions are too fast, baseline may lose detailed motion information, resulting in over-smoothing pose estimation. The figure is the proposed architecture. On the left side, you can see cross-sampled poses, which computed from the pose estimator. These cross samples are passed into cross encoder, and the encoded values are utilized for computing cross attention in RecoverNet. This video is result from baseline. And this video is results from proposed method. Results are very similar. In the baseline GitHub repository, I can find evaluation source code. With this code, I evaluated the proposed method and compare it with the baseline. With respect to MPJPE, results from baseline is better. However, with result to PA and PJP and acceleration, proposed method get slightly better result. My code and contact is as follows. Thank you for listening to my presentation. Goodbye.